So in this video, we'll talk about hypothesis testing in fMRI. First, we'll discuss what's special about hypotheses in fMRI, and then we'll move on to the subtractive method, which is a way basically to deal with the special circumstances of imaging. We'll continue to a note on reaction times, which are part of the subtractive method and how it was developed, but also continue to be an important behavioral variable that's commonly also reported and measured in imaging experiments. And finally, we'll discuss an example experiment that will go over this sort of as an illustration of how the subtractive method is applied to imaging. Now we'll start with some basics here. Obviously, you guys know this already. This is standard stuff. But let's bring everyone back up to speed. So in experimental design, we typically have an independent variable and a dependent variable. And you already all know this. An independent variable is something that we are controlling as the experimenter, and it has conditions or levels. We can have a treatment condition and a control condition, for instance, or we can have different levels of a condition to make comparisons. So in the example that I'm giving here, our independent variable is a state of anxiety that's induced by threatening participants with, let's say, electrical shocks. This is the stimulator that we use for this in our experiments, for instance. Now, we can have a treatment condition where there is a possibility of shock, and you don't have to give it in that condition. You just say, look, there's a red background. This might mean that you might get shocked, for instance, right? And participants know about this. And you can have a control condition. Let's say there's a blue background. And in that condition, you cannot get a shock. So we have one condition where participants might get stressed or anxious, and one condition where they're pretty safe and should not get stressed. And then we can compare behavior in condition 1 versus condition 2. But you can also vary the level of shock. You can have a low, medium, or high level of shock amplitude, which basically could lead to different levels of stress or anxiety. Now, in terms of the dependent variable, we're interested in, for instance, reaction times as plotted here. This is a measure that's very important in cognitive psychology. It continues to be important in neuroeconomics as well. If you just have a look at the video on the drift diffusion model, reaction times have a large importance still and continue to do so, also in the field of neuroeconomics. They tell us something about the strategies that participants are using or how difficult a specific decision can be. But obviously, our main dependent variable in the context of imaging is the bolt response, right? So I'm plotting the bolt response here on the y-axis. This is the magnitude of the bolt response in a particular region. And that's what we want to measure when it comes to imaging experiments. But we can also measure other behavioral variables, like, for instance, the predicted probability of transferring something to someone in the context of a trust game, or even the score on a personality questionnaire, such as the anti-sociality factor here. So we have an independent variable that is what we manipulate as the experimenter. We have a dependent variable, such as the bolt response, reaction time, or trust taking. That is our variable of interest that we want to measure, and we want to see whether our variable of interest changes in a treatment condition where we do something to the participants that's of interest versus a control condition where we omit this, for instance, a safe versus a shock or a threatening condition. We also work with categorical versus continuous variables. Now, a categorical variable would be, in this case, shock versus no shock, whereas a continuous variable would be, let's say, having different levels of shock amplitudes that should lead to increasing amounts of stress, depending on what condition the participant is in, right? Or a continuous variable here is, for instance, the anti-sociality factor, the scores that people have across different ranges. That gives us a range of scores that are possible and that are continuous, and basically allow us to run regressions on these, right? To have these types of correlations here. Then we have different types of designs. We have between subjects designs, which, for instance, are commonly used when we have different types of groups. Let's say we want to compare the neural responses of depressed participants to those of control or healthy control participants. That would be a between subjects design, where across these two groups, they perform the same task, but then we can see, well, how do brains respond in depressed subjects and how do brains respond in controlled subjects? For instance, what are the neural correlates of trust? Are they different in depressed versus control participants? And what's very common and most common in neuroimaging are within subjects designs, where all of the different levels of the independent variable are shown to every single person. And this gives additional power because we typically have expensive studies. So within subjects designs are commonly preferred in the imaging context. But both are clearly possible. You can have different groups of subjects that do different things. So what does it mean to set up a good research hypothesis in fMRI? So there are a number of considerations. We don't just have one hypothesis, but we have multiple ones that we can set up. So in the early days, researchers commonly set up hemodynamic hypotheses. And that means, for instance, the statement that if we add two visual cues in rapid succession after one another, such that this occurs before the hemodynamic response to the first one goes back to baseline, do then these two stimuli, do the neural responses or the bolt responses to these two stimuli add up linearly or non-linearly? So that could be a hemodynamic hypothesis addressing these. We can also have neuronal hypotheses in a sense that we make predictions about the neural activity underlying some treatment effect, although we're only observing the bolt response, but obviously those are related. And finally, and most commonly, we specify psychological hypotheses that relate the psychological state to the bolt response, which we then observe in the statistical map. And that's basically what we're manipulating in our experiments. We're manipulating, let's say, the different conditions under which people trust and how this relates to what we observe in these statistical maps in the end, right, within the brain. So one psychological hypothesis could be that trust involves estimating the likelihood of being betrayed by another person. And this is commonly computed in social cognition regions, such as temporoparietal junction or DMPFC. Now that's a very long one, but that could be one possible one in the field of neuroeconomics. The important point here is that in addition to having purely behavioral hypotheses, we also have neuroanatomical ones. So in what types of regions do we expect activation to occur in our specific task? And we also have psychological and possibly neuronal or hemodynamic hypotheses that we can specify in the context of neuroimaging. Now let's talk about one very common method that's used in the early days of cognitive neuroscience or neuroimaging when it comes to functional magnetic resonance imaging. And this is the subtractive method that was developed by Franciscus Donders, who was depicted here. He was an ophthalmologist, actually, working on the, basically eye. And this was quite in the early days. And basically what he was interested in is, what is the timing of the mind? So how is the mind? Are there different processes within certain tasks that we do that can be subdivided into subcomponents? And this was then referred to later as mental chronometry, because he started measuring the timing of these subcomponents in very simple tasks, which we'll go over in a second. So he was quite influential, actually, in that many scientists up until this point assumed that mental operations basically responded to any kind of stimulus, any kind of task or decision, basically instantaneously. Now, this is clearly not the case. There are different types of processes. Let's say that the visual aspect has to be processed first. Then a computation has to be made about, if it's a binary choice, is one aspect valued higher versus the other aspect, and this then has to be computed in terms of what actions do we have to make to communicate that we wish to obtain the higher valued item. So it was one of the first attempts to analyze basically component processes of simple tasks, and we're in a sense doing this now with very complex tasks such as decision making. So what did he do? So let's take a Donders-like experiment and imagine that you have an array of lights in front of you. Let's say there are 5 lights. They might have different colors, right? Yellow, red, green, blue, etc. And the first task is a simple detection task. So your task is, as a subject, just simply press a button as soon as the light goes on. And then as the experimenter, I will measure your reaction time to this simple task. So you're just detecting something. The second task, I'll ask you, so I do this like, let's say 100 times, maybe 150 times or more, and I record your reaction time every time. Then I'm going to ask you to go home, come back another day, or if we still have time on that first session, we'll do a discrimination reaction time task. Now we have an array of 5 lights still, right? And your task now is no longer to push a button when any light goes on, but to push a button only when the red light goes on. But one button is still the only response possibility that you have. So you just push when the red light is on, and you don't push when any of the other 4 lights are on. And I'm going to do this multiple times with you again and measure your reaction time on this task. And finally, we have a choice reaction time task in which we have an array of 5 lights and 5 response buttons. And those buttons are labeled also red, green, blue, yellow, etc. Right? So the buttons correspond to the lights. And here you have to respond with the button corresponding to the appropriate light. So each button is assigned to one light, and you then have to make the selection and make sure that you have the right selection that represents your button press to the appropriate light. So we have these 3 different tasks, and you can see that they increase in complexity, right? Especially of the behavior. Now, there are a number of predictions that we can draw from this. The detection task is the simplest task. It requires to perceive the stimulus and then simply execute a motor command, right? That's a button press in this case. So it's very simple. How long does it take to perceive and then execute the action? The discrimination task also requires you to make sure that you discriminate between the lights and only push the response button when you see the correct light. Again, there's still only one possible response, so the motor command is quite easy then, right? So it involves all of the above. It involves perception, it involves executing an action, but it also involves a discrimination stage. Namely, is it the target location that was lit up or any of the non-target locations, which takes some time. So by subtracting reaction times during the discrimination task, and we've done this now 150 times, and the detection task, which we've also done 150 times, we get 2 distributions, one that will be taking longer relative to the other one that will be a little bit shorter. And we can then subtract the averages from each other, and you have the average time that it takes to discriminate between the different targets and non-target locations that light up, right? Finally, we have the most complex task, which is a decision where you have to press the correct button assigned to a specific color. And that also involves discrimination. It involves perception and motor stages, but it also involves, in addition to everything else, a choice stage, which is probably a bit more complex. Well, not probably, it is more complex because it assigns the correct button press to a specific light stimulus. So what are the results that he finds? Obviously, we know this already. Simple detection tasks took the shortest amount of time, discrimination tasks took longer, and finally choice tasks took the longest, which indicates basically using the subtractive technique, right, that he came up with, that each of these stages involves more complex mental operations that take longer time. And he can assign specific attributes to these, namely that the detection task involves perception and motor stages, then there's a discrimination stage and a choice stage. So we can make inferences based on the reaction times about mental operations. And this is the part where mental chronometry comes in. Namely, that longer RTs for increasingly difficult tasks must reflect differences in the brain's processing times, but also differences in how complex a certain task is for the brain and what type of operations go into the computations that finally lead to the answer. So this is kind of a neat technique, and it's actually a technique that we use in fMRI. So we make the distinction between a, let's say, treatment condition and a control condition, and then we use the subtractive method to subtract out all of the activation that's involved in the control condition from the treatment condition, which has basically all of the same requirements except for this one additional stage, let's say a choice stage. And then our treatment condition, our control condition would be a discrimination stage. So in fMRI, we want to have one condition that has all of the perceptual elements, that has all of the motor elements, and possibly all of the discrimination elements, but it doesn't involve the specific choice elements that we're interested in. Let's think, for instance, about the difference between, in this case, the non-social condition, the risky control game here, or the risk control game, asking participants to make decisions about investments in lotteries, and a social condition in which we make exactly the same kind of decision, but we're actually investing into another person in the context of a trust game. So what we have here is basically a subtractive method. We're matching everything in the decision screen, so the perceptual elements, we're matching the motor elements, it's exactly the same choice. We're even matching the type of stimuli, so the type of values that participants can and cannot transfer in each of these tasks, except for this one element, namely you're making a social decision in one condition and a non-social decision in another condition. And so when you subtract the activations, the neural activations, or the imaging responses in this condition to those in this condition, the only thing that should be left over is the aspects or the additional aspects that are involved in when you make decisions in the context of a trust game. So from this example, we can see the effects of cognitive subtraction in action. Right? It's a simple example contrasting a social versus a non-social condition. If the experimental and control conditions differ in only one dimension, then the subtraction will reveal the contribution of the change along that dimension alone. And we can apply this principle of cognitive subtraction to fMRI if we have two conditions and we contrast them to each other. Then we will find activation in regions that respond specifically to the experimental condition, with all the effects of the control condition on the brain being removed from the activations that we will see. So we work with contrasts. fMRI is in principle a relative experimental approach because there's no perfect baseline in fMRI. So then when it comes to setting up our research hypothesis in the imaging context, then what we want to do is, we make the assumption that a change in the independent variable obviously leads to a change in the dependent variable. We have an experimental condition that manipulates the independent variable. It contains the task or the stimulus that we're interested in, let's say the trust game, which has this social component. And then we have a control condition that provides a standard to which the experimental condition can be compared. Let's say a risk game that has everything else. It has the same visual screen, it has the same values, it has the same motor demands, so you have the same choices. But it differs in the effect of interest, namely there's no other person involved, it's just an algorithm that transfers the money back. Let's consider this other example here, namely face perception, which was studied extensively in the late 90s by Nancy Canvisher and her colleagues. And the goal here was to try to find a neurobiological basis for face perception. So what's the regions in the brain that are involved in face perception in particular? And this is an interesting question because obviously faces are very important to humans. We see faces all the time. We infer identity from faces. We make predictions about behavior based on faces, and we even assign character attributes such as how trustworthy people are or how dominant people are. And all of this can happen automatically. So it's an interesting stimulus, and it's important to understand what the brain basis of this is. Now, obviously, in an experiment like this, we're going to use experimental stimuli like these, right? We're going to use faces. We'll take out the hair because that gives us information about the type of person this is, which we don't want in here. We want to control for that. And then let's consider the first control condition here. Namely, we're going to compare when participants see faces, so all the time periods where participants see faces in the experiment, to a control condition when they just see a blank screen. The question is this a good control condition? Now, the contrast would reveal regions involved in face perception, but not specifically so. There's a lot else that would happen, right? Well, let's consider what all this other stuff would be. Much else would be activated here, and you would basically get something like this, so an activation that involves all of these other things, namely all stimulus and task-related activity during seeing faces. I don't know if the subject was asked to do something we didn't specify earlier. Maybe they have to push a button and identify whether the face was male or female, which is commonly done. So to keep the participants busy while they're doing the task and not make it such a boring task. But everything else that goes on when people see faces, they might have some emotional reaction to it. They might even, as we've seen in other parts, they might even have reward-related activity to very attractive faces and less to non-attractive faces. Or they might have amygdala activation if they're threatening faces, for instance, or if their facial expressions are not very positive. At the visual level, so in visual cortex, we'll have activations due to the brightness of the faces, due to the different edges, which also have specific types of neurons that code for these kinds of things. So we'll see a lot of visual activation, such as shown in this example here. At the task activation, we would have all the types of motor demands, all the decisions that the subject has to make to fulfill the task. All of this would lead to differential activation that our control condition does not take care of. We'd have attention differences. When you see faces, you would pay much more attention to the task than when you just look at a screen when you're bored. And a number of explicit and implicit processes that would be going on. So implicitly, even if you ask the subject to do a task, they can be doing many other things. And this might happen more when subjects aren't asked to do anything. So they can start thinking about what they're going to do after they're out of the scanner, what they're going to have for lunch, or how they're going to pass their next exam. So there are all sorts of processes that are going on that we're not controlling for with this control condition. In fact, we'll talk about this in another video when we discuss the default mode network. Let's consider two other control conditions. Let's consider scrambled versions of the stimuli. They are matched for spatial frequency and they're matched for brightness, right? So those are scrambled images here. But nonetheless, they are meaningless stimuli. So this is basically, so now you're controlling for the visual activation, but you don't have any higher order meaning. So there's no object perception involved. They're just simply meaningless patterns. There's nothing you can attend to on these types of stimuli either. A black area here or a bright area doesn't tell you anything about the underlying meaning of the stimulus. So there's still an issue here with the meaning. And most likely you can't perform a task on this. So you couldn't identify whether this is male or female, or whether this can be used with the hand or with the eyes. So there's no true task that you can perform on these types of stimuli, at least not something that comes to mind quite easily. So that's also not a very good control condition. At least, however, it controls for the visual aspects of the activation. So you would get rid of the visual activation here that's not related specifically to face perception. Can we make a more specific control condition? The third one would be non-face objects. And that's actually probably the best one out of the ones we consider here, where you show objects that you can clearly identify and that clearly have some meaning that you can associate with this, but that are, instead of being social stimuli, that are non-social stimuli. And this would reveal then areas of the brain that respond more to faces than to other types of objects, or sort of social regions within the visual system versus non-social regions within the visual system. That's probably the best condition that we can think of in this scenario, and a good control condition when we want to identify specifically those regions that are involved in face perception. So you can see that cognitive subtraction is somewhat difficult, because what we have to do is we have to match two conditions just along one dimension. If the experimental and control conditions differ in only one dimension, then their subtraction will reveal the contribution of that change along this dimension, right? That's what we want. But it's difficult to match these dimensions of interest. And we've seen that difficulty in the previous examples before. And the question that is often asked, is it even ever possible? Because any factor that is not completely matched will be a possible confounding factor and might not reveal the specific activation due to one condition compared to the other condition. And this is something that requires a lot of thinking on the side of the experimenter to obtain this good or near perfect experimental design that then eliminates these confounding factors. Let's consider some confounding factors to make this aspect clearer. We cannot reduce all confounding factors. So what we're doing is, typically, we're using randomization within our experiment, or some form of counterbalancing or matched balancing to account for this. Here are some factors that vary within the experiment, and these ones should do so randomly. Now, that's also very, very difficult, obviously, right? So we have practice effects. So as you start getting used to what the demands of the task are that you're doing in the experiment, you will get better at it. But you'll also get more and more bored because it's not a new task anymore, and you might actually find a heuristic after some learning. So let's say at the first third of the experiment, you're basically figuring out, what am I doing? Am I doing this right? And then you get into sort of a state of where you just use heuristics. That's kind of good enough to answer what the experiment is asking of you. You also get more and more tired throughout the experiment as a subject. A subject might lose motivation. They might put effort differentially under different conditions. Interesting conditions might lead to more effort, not so interesting conditions to less effort, and people make mistakes. Now we want to randomize the effects of these confounds as much as possible, and for this we can use counterbalancing. For instance, when complete randomization is not possible. And that's one way, for instance, to control using these types of counterbalancing designs, where we have, at least we're controlling for the order effects. So we have condition A followed by condition B, then by A and B again, and in another subject we would do, we start with condition B, then condition A, B, and A. And this kind of counterbalancing would then at least control for the order effects across subjects. So this is something we can do using good experimental design. Randomization may not be possible, for instance, because of time constraints and because of constraints that that are specific to the experimental design requirements of functional magnetic resonance imaging. And here's one of such sort of limitation that we face. So typically, we break fMRI experiments into separate runs, which is apparent when you look at fMRI data. You typically end up with data that gives you separate data sets, separate nifty images for run 1, for run 2, and for run 3. And there are a number of reasons for why we do this. One of them being that we want to make sure to check in with the participants every 10 minutes or so. Give them a bit of a rest, talk to them a little bit, let them wiggle their toes, and those kinds of things. So one thing we shouldn't do is the following. Let's say we have 4 conditions, condition A and condition B, and then condition C and condition D, right? What we can't do is have A and B appear in run 1 and condition C and D appear in run 2. There are a number of reasons for this. First of all, we have signal drifts that can be different between run 1 and run 2, and so we can't properly remove this. So that means that condition C and D might lead to much greater activation than condition A and B. And then when we compare this, without properly removing this, we end up with the conclusion that, well, obviously C and D lead to more activation than A and B. And that's just simply due to the properties of the scanner, which we don't want. There might also be practice effects. So performance during run 2 could be better, or there could be fatigue effects. So performance during run 2 might be worse in that case. So what we want to do is we want to make sure that all 4 conditions appear in run 1. So we have A, B, C, and D. This might lead to a little bit of a longer run. And then we want to make sure that, and a run that also involves only these 4 conditions presented once or just a couple of times. So we want to make sure that we randomize and counterbalance the order of these events within the scanner. So randomizing or counterbalancing conditions such that all are affected similarly on average is a key here. And we shouldn't do this across 2 separate runs. So finally, let's consider a caveat of the subtraction method or the pure insertion method. So let's consider a task, just a simple task. Let's say we're identifying emotions on facial expressions. And then we add a component to this task. So in one condition, we're just doing neutrally identifying emotions. In the other condition, we're doing this, let's say, after some incidental emotion has been triggered by some stimulus. So we're adding a new component to the task, an emotion. And then what happens to the old task is we're not just having the initial task and the new emotion, but we also have the interaction between these 2 components. So the initial task and the emotion manipulation that we added to it. So it's not just 2 separate things that we're doing, but we also then adding interactive effects between these different types of tasks that we're adding to one another. So the important thing here is that we end up with an integration or interaction effect that can be considered a third or a new component that was added just by adding another task, in our example, an emotion induction. So Carl Friston has said, therefore, that this renders cognitive subtraction a rather unsound conceptual basis for many, many lines of research. So depending on what we want to achieve, cognitive subtraction might not be the best approach. So let's consider this again. Let's think about this image here. And then this is an image. Let's assume that this lady is expressing surprise, right? So like, what's happening here? It's surprise, which is a neutral emotion when it comes to valence, right? So we have positive emotions, we have negative emotions. Surprise is somewhere in the middle. It's just, wow, something happened, but we don't know what. And then if you give participants, if you place participants in emotion induction, let's say you induce anxiety. Participants might then interpret this phase as a fearful phase. Someone who is also like in your state, because you're now in the state of fear or anxiety, you are much more likely to interpret other people's emotions as well. She's similar to me, so she's going to express fear here or anxiety in this case. If, however, you induce happiness, then you could say that, well, something good must be happening to this person. She's probably expressing surprise because she just gets surprised by all of her friends who are throwing her a surprise party. So it leads to these interactive effects that can actually lead to different interpretations of the stimuli that you see, depending on what condition you're in this second task, in this new component here. There we're talking about integration or interaction, which can have many different effects on how we perform a task, which I hope this example of the emotion manipulation made clear. So the picture commonly is more complex than pure subtraction, especially things that we're actually interested in, things that have higher ecological validity. For this, we have solutions. We have factorial designs and we have parametric designs. And parametric designs are particularly common in the field of neuroeconomics, and we'll talk about those in much more detail later.